Hello, my name is Donghyun Ko, and it's my pleasure to present today FlexBoard, a flexible breadboard for interaction prototyping on a curved and deformable surfaces. I did this work together with my amazing colleagues Yoonji Kim, Junhee Ju, Michael Risley, and Professor Stephanie Miller from MIT CSAIL. I want to get started by directly showing you what a FlexBoard is. FlexBoard enables prototyping with interactive components like various sensors, LEDs, and displays, similar to a traditional breadboard, while also being highly flexible. This enables FlexBoard to be used in interaction prototyping. FlexBoards can be bent around curved geometries and let makers place input and output components at their preferred location in an angle that fits to the base geometry. FlexBoards are customizable in their shape. Multiple FlexBoards can be attached to each other to form a larger prototyping area. To achieve this, we integrated ball joints at the edges. FlexBoards can also be customized in their length by simply cutting them. FlexBoard can be also attached to flexible material like fabric. Here we see multiple FlexBoards on a VR glove that can bend with the user's hand while being in use. Makers can easily change the location of each component while testing the functionality of a VR glove in situ. In summary, interaction prototyping directly on the physical user interface let makers and designers explore new user interface design and test them in practical use cases with real users. However, as you can see in the example on the left, the traditional method for testing interactive components is to attach them with glue and long wire on the prototype, which make them hard to relocate and quickly go through multiple design iterations. A popular prototyping platform for prototyping circuit is the breadboard. While it lets users quickly change circuits, it is not well suited for interaction prototyping. Since it is rigid, it is difficult to attach to curved geometries. Mounting components also do not follow the curvature of the object geometry, as the breadboard is flat and rigid. Alternatively, makers can use smaller breadboard which improves mounting components, but still has limitation, especially when mounting many breadboards on inward bend geometry, as we can see in this example. Also, designer can directly glue or interactive components with tape on the object and use long wire to connect them to the main circuit on a breadboard. However, this method is not ideal in all cases, as wires can frequently disconnect and the additional breadboard might hinder mobility. Finally, some makers solder female header pins onto flexible protoboard, but such boards can only bend in one direction, which limit their applicability. Supporting makers and designers in interaction prototyping has also been the focus of inspiring research in the past. As an example, BitBlock suggested modular mini breadboard that improve interaction prototyping, but were still rigid. Zhu and colleagues proposed a CuffBoard, where the breadboard layout is directly integrated into a 3D printed copy of the prototype. Finally, rubber breadboard and jellyboard are closest to our research and demonstrate silicon cassette patches that use conductive materials in a breadboard layout. However, they have to be manually casted. It is difficult to adapt their size, or they show limited conductivity. In contrast, FlexBoards can be digitally fabricated using a 3D printer. They are customizable in shape by cutting and joining multiple FlexBoards. Since we reuse terminal strip of a regular breadboard in our design, they offer the same conductivity. We also designed FlexBoard to support the standard pin spacing of 2.54 mm when being flat. And finally, FlexBoards are highly flexible both in upward and downward bending. Let's dive deeper into the mechanical design of FlexBoard. Flexible structure is based on traditional living hinge, which allows it to be bent. Each hinge structure holds one terminal strip that are embedded in existing breadboard while keeping the standardized spacing. We added bridge structure to the base living hinge design to tightly hold the terminal strip even when bent. FlexBoard can be easily fabricated. After 3D printing the FlexBoard structure, users can simply embed the terminal strip into the living hinge. As you can see, while keeping terminal strip, FlexBoard can bend up to 12 degrees per hinge, either downward or upward bending. I will now demonstrate how FlexBoard can be used in prototyping with three scenarios. The first one is prototyping on a VR controller. We first created an initial prototype, which includes various sensors to alert users of potential collision while in use. We conducted an in-situ test with the initial prototype, and we discovered a blind spot. We directly iterated by changing sensors. Also, we moved vibration motors to the little finger, and we added a buzzer for better notification. It allows us to make a well-functioning final prototype. The next example is prototyping on a deformer glove for development in VR context. First, we cut and assemble FlexBoard, and then we sew the assembled FlexBoard on a glove. As a result, we could make a glove-type prototyping platform where our user can freely make hand gestures. While wearing this glove, it is possible to add components, test their gestures, or even modify the code. We made this final prototype, which senses users' pulse signal or movement of the wrist and fingers. The final example is prototyping on a curved kettlebell. This is an initial prototype that senses users' posture and count repetition while working on it. We found that the sensing was not stable and displays were not fully visible. To find the proper positions for the components, we added additional FlexBoard to the surface. This enabled us to explore the optimal position of the components. Now, as you can see, this time prototype is functioning well. FlexBoard has been evaluated in various ways to prove its practical use. Firstly, we evaluated the flexibility of FlexBoard in both upward and downward direction. As previously mentioned, FlexBoard can be bent up to 12 degrees in both directions. Next, we also tested the adherence of the FlexBoard to a curved surface using various adhesives. The results show that double-sided tape, epoxy, and Velcro tape provide stable adhesion to a wave curvature for up to 24 hours. Moreover, according to the test, the FlexBoard can withstand more than 50 bends when adhering to a flexible surface. Finally, we tested holding force of the FlexBoard when electronic components are unplugged. Even when bent, the FlexBoard has a similar holding force to that of a conventional breadboard. Despite these many advantages, the FlexBoard also has some limitations. First, the bendability of FlexBoard may be reduced when larger and rigid components are plugged in. Also, it is not very feasible to prototype on highly curved geometries. Moving forward, we aim to improve the fabrication speed and cost of the FlexBoard with injection molding techniques. We also plan to study the prototyping workflow that can be affected by FlexBoard. And finally, we want to extend this functionality, such as shape-aware feature or customizing the bendability with functional filaments. This is the end of the presentation. Thanks for listening and enjoy the rest of Kai.